Okay, so first I want to thank the SOC for this opportunity to talk about NIRPS. I'm doing this talk over on behalf of the NIRPS consortium. NIRPS is a near-infrared spectrograph and it has a large team, a core science team members of about 30 people plus 30-ish collaborators and growing, so about 60 people. So our top level requirements is we cover the wide JH band. It's fiber feed from AO and with resolving power better than 80,000. Our goal was 100,000. We don't quite there, but and as any EPRV instrument, we're aiming for 1 meter per second performance. And of course, this is a simultaneous operation with NIRPS. And the baseline data pipeline is the Espresso, modified for to be used at infrared wavelength. And we have a belt and suspender approach. So we have also the EPRV pipeline, which was designed for Spirou. And EPRV is really meant to be portable to other instruments. So I invite you to go and see the poster by Neil Cook, who designed that pattern, which represents several years of work that was designed for Spirou. So this project really started off back in 2014 and 15 when both Canada and Switzerland and France were submitting proposal to do a southern version of Spirou or like, and it ended up to be NIRPS. So you have the milestone here. The pandemic, of course, like everybody else hit us, but finally we got first light last June, and the science operation will actually start in a week. So we're very excited about this. Okay, so this is the NIRPS subsystem. So again, an AO system. We have two modes, high efficiency modes, which is basically an octagonal fiber with a footprint of 0.9 arcsecond in the sky, reformatted with a simple pupil slicer into a rectangular slit. And the high efficiency mode, meant to have a better resolving power. We were aiming to get 100,000, but we ended up getting about 86,000. And in fact, now the trade-off between throughput and resolving power means that probably the HE mode will be the most efficient mode, especially for relatively faint target. So just the pictures of the hardware, the AO system, fiber structure, the prism carousels, and the new shell grading. We had some issue. Our initial grading was from Bach. It's a very coarse grading, 13 lines per millimeter. It was very hard to do. But now we have a new shell from IOF, which has basically almost perfect theoretical efficiency, close to better than 70%. A fiber structure, calibration unit, etc. Okay, so this is also the picture of NIRPS with a fisheye camera back in the Coody room at Lecia. We're showing all the major subsystem. And we had the first light last June. I was not there, unfortunately. François Bouchy, the other co-PI, was leading the show. I was myself busy in Baltimore finishing commissioning of NIRPS. So it was a very exciting time. But you can see this is an AO system. You can see the reference sensor in there. And one thing I'm going to talk about, we can do actually AO scrambling, which is very efficient to beat modal noise. Okay, so wavelength calibration, we have the usual allocated lamp from Uran Neon and EPRV. All of that has a very good solution. We have an LSC, which is currently under development from Menlo. This is led by François Bouchy, and we hope to have that on the sky, hopefully this year. But anyway, the instrument is show very nice stability. In fact, the instrument is so stable that we're seriously considering not using the EPRV. In fact, the nightly calibration with the allocated at the beginning of the night and the end of the night is actually sufficient to get to the 1 meter performance. Thermal stability. So this is a plot of the thermal stability over 3 months. We're achieving some millikelvin accuracy. This plot is a bit misleading because this is a point, we have several control points, and this is one where we have both a temperature sensor and a heater. But if you look at an optical element, which is the grading, which doesn't have a heater, you can see that the temperature is fluctuating by a few millikelvins over 3 months, and which seems to be coupled with the room temperature. And so because of that, we're actually now building a very simple thermal enclosure, similar to HARPS, but simpler, which we believe will damp the the room temperature variations to minimize these variations. You can see sometimes we have some power cuts and cryo cooler goes off, but we rapidly recover. But overall, we're very happy about the thermal control. Modal noise. So that's one of the surprise or from NIRPS. So we basically have this fixed pattern noise that we can't really well, we can correct it thanks to both AO scrambling. So we have a diffraction emitted PS of about 0.13 arcseconds. In high efficiency mode, it's about 0.3 arcseconds. So we actually just during an exposure scan over to scramble. And there's a nice poster by Yolanda French to describe all the details performance of this during commissioning. The short story is that both AO scrambling and the scrambler reduces the modal noise by about a factor of 5 to 10, depending on the mode. And it's like a quasi-static speckles in imaging. This thing is relatively stable over several days. In fact, we can actually calibrate them out further using fast rotating hot stars, that we use anyway for telluric correction. Okay, so this is the spectrum of Proxima showing the whole wavelength range. So again, the measured resolving power at the high efficiency mode is 84,000, 70,000. And of course, this is always getting both ARPS data simultaneously every time we observe. And we have also now the NIRPS connected to Elias. This is an effort led by Xavier Dumus. And so this is the recent data. We're just right out of the box. And the actual data from Elias with NIRPS, if you've been a little bit, you're getting down to 2 meters per second. So this is very exciting. We have a new infrared eye on the sun thanks to NIRPS with Elias. Okay, so preliminary results. This is Proxima, which will definitely be one of our radial velocity standards. And so this is essentially right out of the box data. There's no fancy data analysis, no GP. Of course, telluric subtractions, RV data from the line by line techniques, which I invite you to learn about by Etienne Artigot. And so you can see, so the dashed line is the ephemeris from the espresso data, and there's a slope probably related to the rotation period of Proxima, 90 days. So that's it. Typically, the RMS here is about 1 meter per second, but when you take into account the phone noise, the RMS is actually more like 70, and that's right off the telescope. So we're extremely pleased with these results. Another example is famous multi-planetary systems. So it's only a few data points, but of course we'll observe this target further during our GTO. So performance are very good. Water detection. So I'll talk about very briefly about our GTO programs, but a very significant fraction of our GTO will be dedicated to atmospheric characterizations. And this is a target that had been observed with Peru. Over 3 transit to detect water, and here during commissioning only one visit, and we get a clear water detection of about 5 sigma. So we're extremely pleased by these early results. Of course, this instrument is not just for PRV. Surad had a question about abundance. So this is a demonstration that we can determine not only metallicity, but refractory element fairly accurately. Of course, there's caveats about models and there's details here, but the data is there. This is an example with LHS 1140, which was observed during commissioning, and you can see we're actually measuring the iron abundance, silicon, and magnesium, which are the basic material for internal structure models. Now let's talk about science. So our NIRPS main science case is detection of exoplanets from M dwarfs, active in young stars. We're very focused on looking at M dwarfs early, close to the sun. These are targets that we'll want to image with ELT and TMT. I'm not going to go through the details, but the main message here is that we are allocated 725 nights over 5 years, and this will start in fact next week. So we're very excited. Okay, so just a bit more in details. So again, we are very much focused on M dwarf for the PRV work, and our time is distributed roughly equally between 3 work packages. 1 is the blind searches, 2 is transit follow-up, and 3 is atmospheric characterizations. So very briefly about all 3. There's we had a series of white papers from the team to propose ideas, and so there's an example here where we're going to, of course, look at the very nearby M dwarfs to improve the architecture of nearby planetary systems. And again, this is a very important programs to provide targets for the ELT. By the way, Andes is currently under PDR, so this thing will be around by early next decade. Gaucho, this is a program to look at late M dwarf. This is a nice diagram at the bottom showing the planet mass versus the effective temperature around which planets are detected. And of course, there's a dirt below 2000 Kelvin. We don't see much, and that's likely a selection effect. And we need infrared data. And Pascal showed this very nice plot showing the importance of the power of infrared to discriminate between stellar activity and Keplerian signals. So this is going to be a very important programs. And we're looking also at young stars. Work package number 2. Lots of things. We're very much focused on trying to understand the Fulton gap and master, and also on a few targets to not be content only with 5 sigma detections. We want to get very detailed mass measurements, and so to get constrained on the core mass fraction, and in some cases water mass fraction. So lots of programs here that will keep us busy for 5 years. At the bottom is an example of targets that we observed during commissioning. So it just shows that the instrument is performing extremely well. I invite you to look at the poster by Charles Cadieux about the LBL reanalysis of espresso data, which gives us a 3% mass measurement of both planets, and less than 2% in the radius, and that changed the whole picture of the system. And so this target will be observed again with NIRPS. Okay, so atmospheric characterizations. This is most of our time will be to do transmission spectroscopy, but also eclipse spectroscopy. This is we're going to have for the next 4 semesters about 90 targets that will be observed. This work is led by Romain Allard. So on this, I'm going to conclude that after 20 years of success with HARPS, HARPS as a sister. And she's been crawling for the last 9 months, and now she's actually walking and ready to run for the next tide of big that will come next weeks. Thank you very much.
Thank you, Rene, also for keeping the time. So are there questions?
Thanks for that great talk. Question on the model noise. Do you have a measurement of the signal noise ceiling because of the speckles?
It's about it's increment, so it's about 0.2%. So we're down in the photo noise. Once we apply the corrections with the fast rotator, it's down in the photo noise.
Is one there?
Thank you. Good talk. What is the typical storage ratio of NIRPS? And my second question is, I'd like to know what is the typical V or R-band magnitude to get good fiber injection.
Sorry, I didn't quite get the question.
So first question is, what is the typical storage ratio?
Oh, the typical Strel ratio is about 0.3, 0.4.
Okay.
Yeah. We're not really limited. I mean, for a typical target, we want to look at tests. I mean, we can lock on very faint target. We observe the lumen 16, for example. Yeah, and of course, with degraded AO performance, but we can observe that using the high efficiency mode.
I think there was one last question, yeah? Jen?
One from Slack from Andrew Howard. The details of the NIRPS shell grading went shell grading went by quickly. Could you say more about the dimensions, vendor, quality, etc.?
Okay, so the first shell was from Bach research, which ended up not having some issues, and we had a backup solution with IOF in Jena, which is a different technology using a silicon substrate, with etchings, And the measured efficiency is about 70%, which is close to the theoretical of 80%. So we're extremely happy about that. Yeah.
Thank you very much. I propose to stop here and